In previous section of the course, where we've used method of joint to analyze trusses, we've noticed that the problem solution technique is very laborious. So what we're going to do in this section of the course is look at method of sections. Method of sections uses techniques from rigid body equilibrium that will help us to identify the internal forces in a small number of truss members. If you need the forces in every single truss member, then maybe the method of joints is easier to use. But if you only need a small number of internal forces, say for instance you only need the maximum forces, maximum tensile forces, maximum compression forces, then the method of sections can be a quicker way of getting at those forces. So we're going to just introduce this topic by way of an example. So we have a truss structure here that has 6 3-meter wide bays. We have a 10 kilonewton external load, and it's simply supported. So to get this procedure started, we're going to treat the whole body, the whole truss, as a rigid body, and we're going to calculate the reaction forces. So we'll just draw the free body diagram, and we can consider the whole truss as just a block. We don't care what's going on inside the truss members at this moment in time. That's point A, and we have a roller at point G and the point load in the middle. So that was 10 kilonewtons, and now we'll add some dimensions to this. So we had, and add up numbers, now we have 9 meters and 9 meters. We don't really need the vertical for this one, so let's do the equilibrium of this rigid body. Finally, just remember that this was point G. So sum of the forces in the x direction for the equilibrium of the entire body. So we've got, and we'll just draw on the reaction forces. We have a vertical reaction force at G, vertical reaction force at A, horizontal reaction force at A. So let's call that one RAX. This one we'll call RAY and RGY. So some of the forces in the x direction, RAX equals 0. There's nothing else there. Let's take the sum of the forces in the y direction now. So we have, and we're going to exploit symmetry in this situation. So we have RAY plus RGY equals 10 going down. And from symmetry, we can see, looking at the symmetry of the full body, for 50% of the load must go to G, 50% load of the 50% of the load goes to A. Therefore, RAY equals RGY, which equals 5 kilonewtons. Okay, so now we have the reaction forces. We're going to go back and look at our truss. Now, in this problem, we're told that we only need the forces FEF, and I'm going to mark these up as we go along. So FEF, we want this force. We want FEM, which is this bar here, and we want FLM, which is this bar here. So there are 3 bars. And what we're going to do to solve this problem is we're going to make a cut where we need the forces. So I'm going to just make a massive cut and cut the beam into 2 pieces. And then what I'll do is draw the free body diagram of either the left-hand side of the truss or the right-hand side of the truss. So let's go ahead and do that. Before I do that, it's worth noting that we don't really care about any of the internal forces. Therefore, we can consider this just to be a rigid block when we draw the free body diagram. And again, on the right hand side, We don't care about any of the forces, for example, Fmn, so therefore we can consider this just to be a rigid block, which considerably helps or speeds up the process so you don't have to go along drawing individual bars in the system. So let's go ahead, draw the free body diagram of the right hand side. And so in this case, let's look what we had. So we had this square or rectangular section FGNM. And we had a reaction force, a vertical reaction force at G. Now, where we have the bars coming away from joint M and joint F, we're going to draw tensile forces from those bars. And it's easier if you imagine, we'll go a dotted line, where we continue the rest of the structure as though it's not been cut off from where we are. So these would be point F, point M, and point G, where we have the reaction force, and for completeness add in the extra point N as well. So we've got dotted lines, and this is where, and I'll put them in different color, where the point E would be and the point L would be, but they don't actually exist because we've cut that away from the structure. But this does help us, but at point M, we have a force going in the direction to E, and we're going to presume that it's acting in a tensile manner. We also have a force going from M, acting in the direction to L, and we have a force at F in a horizontal direction or acting along the direction EF. And we're presuming this is tensile. To complete this free body diagram, we need to know the dimensions on the system for completeness. I'm going to go all the way to E, but it's not necessary. So we have 3 meters, and the vertical distance NG was 2 meters. Okay, so now with that free body diagram on the right hand side, we can now just perform rigid body equilibrium to try and calculate the forces on that system. So let's even label this. That is FLM, this is FEM, and this is FEF. Okay, but we're perfectly reasonable that we could choose to draw the free body diagram of the right hand side as well. So let's go ahead and do that as well. So the free body diagram of the right hand side, let's draw that system. So we have 4 3-meter bays. I have to draw this one at a different scale to get it on the page, but we have 4 3-meter bays. So we had a reaction RAY, potentially, although we know it will be 0, RAX. We had, at some distance along here, we had the external load 10 kilonewtons, and again applying the same procedure, imagining the next bay along still being there. So this would be L, and this would be the point E. But we can imagine now that we still have the force FLM. We have the force in this direction, which is FEM, and the force in this direction, which is FEF. So if it helps, sometimes you might want to put M and F label of the joints that no longer exist on the system. To complete the free body diagram, again, we need to add dimensions to the system. So we had 2 meters vertically, and horizontally we need the dimension going all the way to where the 10 kilonewtons was, which was 9 meters away from A, and then we had a further 3 meters before we reached the point E. So we have two free body diagrams. Just to emphasize, we don't care what's going on inside, whether there's any bars or not. We're treating it, each thing, as though it were just a rigid block. Okay, so with the free body diagram set up, we can now go on to solve the problem. And to solve the problem, we need to choose which of these two free body diagrams we wish to go with. So if we look at the free body diagram on the right hand side, we have the three forces coming from the bars and one external force, which was RGY. Whereas on the free body diagram on the right hand side, we have two external forces, i.e. the reaction and the load, and the three forces. So the right hand side is slightly easier. Oops, there is the left hand side, not the right hand side. Apologies. Okay, so we're going to go with the free body diagram of this right hand side for solving the system. And what I'm going to do first, if I look at the point M, I have forces FLM and FEM which go directly through point M. So if I take moments about point M, there is no lever arm to these loads. So if I take the moments at point M and set up my equation of equilibrium, I have the reaction RGY multiplied by the lever arm of 3 meters minus, so going in the other direction, I have FEF, and the lever arm now is the 2 meters, and if it's in equilibrium, the sum of those will be 0. And therefore I can rearrange this because I know RGY already, I've calculated to be 5 kilonewtons. Rearrange this, substitute for RGY, rearrange the equations, and you'll get that FEF equals 7.5 kilonewtons. So we have one of the forces already. Now we have two more equations of equilibrium we can play with when examining this rigid body equilibrium. So we're going to sum the forces first of all in the y direction. However, before we can do that, what we do need to know is, to be able to get the sines and cosines, we need the length of any of these horizontal members. In this truss, we're lucky, they're all the same length. And so we can get, so it's just a quick calculation of it, length EM, so I'll use L for length, equals square root of 2 squared plus 3 squared equals the square root of 13. You might want to leave it in a square root format, or if you've got it stored in your calculator, maybe it has 3.606. Remember, you can get round up errors if you cut your numbers down to maybe one decimal place too early. Okay, so now let's proceed to sum of the forces in the y direction. So sum of the forces in the y direction. And so we have, looking at the rigid body diagram, we have RGY pointing upwards minus, now we have FEM here pointing downwards, and we need to have the proportion of FEM that's in the vertical direction, and that is going to be 2 over the square root of 13. And for equilibrium, that's all equal to 0. So we can rearrange and substitute for RGY in the process, and we'll get that FEM equals 5 times root of 13 upon 2, which equals 9.01 kilonewtons. So at this point we have FEM and we have FEF. Now we just need FLM. So we're going to use the final equation of equilibrium that we have left. Just create a bit of space to play with here. And so sum of the forces in the x direction. So sum of the forces in the x direction now. We have, let's have a look at the free body diagram. We have FEF pointing to the left. Pointing to the left, we have FLM also pointing to the left, and we have FEM also pointing to the left. FEM all pointing to the left, and FEM we have to have the component of that because it's at a diagonal, so that is 3 over square root 13 and must be equal to 0. Now I could put all of these as negative to begin with to show that they're pointing to the left, but then what I'm going to do is multiply the whole equation by -1 on the left hand side and the right hand side, so they simply become positive very quickly. Okay, and we can rearrange all of that and substitute in the known values we have. So we're looking for FLM, so we need to rearrange for FLM. So we get FLM equals minus FEF, then minus FEM multiplied by 3 over root 13. And that gets us, substituting the values that we know, minus 7.5 minus 5.13 over root 2 multiplied by the direction 3 over root 13. And it's one of the nice things, if you leave stuff in square root format, with the square roots are going to cancel themselves out. And so now we get that FLM is equal to minus 15 kilonewtons. And as usual in statics, it's always, even though we have the whole system solved, we have FLM, FEM, FEF, the three forces we were looking for, we always want to apply a double check. So what I suggest you do to make sure that these numbers are correct is generate another equation of equilibrium, and we can do that by taking moments. And if you take moments around point F, you will get rid of the force FEF straight away and the vertical component of FEM. Okay, so after you've applied your self-check, then the solution is done. One thing to finally note, when you apply the method of section technique to trusses, you're limited to cutting at most 3 members. So if we go back to the top, here we cut through the 3 members FLM, FEM and FEF. If you have 4 members, you have 4 unknowns in the system, but you only have 3 equations of equilibrium in 2D to be able to solve the system. So you can only cut 3 members at a time.